All right, let's get into it. Today, we're basically detectives. The crime scene, it's your phone, and the victim is a slow, freezing app that's just, well, it's driving users crazy. Our investigation is officially underway.
So every investigation starts with a key piece of evidence, right? For us, it's this, that feared application not responding dialog. This is our smoking gun. It's the final, absolute proof that something has gone horribly, horribly wrong inside our app. But the real question is, what leads up to this total system failure?
Okay, to crack this case, we've got to understand the evidence we're looking at. We're going to focus on two terms that make every developer just cringe: ANR and Jank. They are related for sure, but they represent totally different levels of failure.
Let's break it down. Think of an ANR as the app having a full-blown heart attack. It's completely frozen, game over. Janky frames, though, those are the thousands of tiny stumbles that happen before that. You know, every single time an animation stutters or a scroll just isn't silky smooth. That's jank. It's death by 1,000 cuts, and it's what ruins the user experience long before that final crash.
Now, you might be thinking, isn't this an old problem we've already fixed? But get this, it's actually getting worse. The data here shows that on the exact same hardware, the percentage of janky frames more than doubled, going from Android 11 to Android 14. So what does that tell us? It tells us that modern operating systems are demanding more efficiency from our apps, not less.
So, now that we've surveyed the crime scene, it's time to line up our suspects. And our number one, most common culprit is the one doing all the heavy lifting you can see, the main thread.
Look, modern phones are absolute powerhouses. They've got 8, sometimes more, processor cores. That means they're built to do a lot of things at once. So forcing all of your app's hard work, processing data, fetching things from the internet, onto that one single main UI thread, it's just an incredible waste of power. It really is like having this amazing 8-piece orchestra ready to go, but you're only letting the violinist play. The other 7 musicians are just sitting there completely silent. So the fix comes down to how we talk between our background workers in the UI. This slide just nails the difference. Using synchronize is like the background worker screaming, "Everyone stop," and just waiting for the UI thread to be totally free. It creates a massive bottleneck. But Q is different. It's like leaving a polite sticky note. The worker just says, "Hey, whenever you get a second, could you show this?" And then it gets right back to its job. It's non-blocking, and it keeps the whole system flowing smoothly. All right, on to our next suspect. This one is way more subtle. A real sneaky villain that works in the shadows. Memory mismanagement. It doesn't always leave obvious fingerprints, but man, it can grind your app to a complete halt.
You see, the big problem with some older memory managers was this thing called a global lock. Just imagine a really crowded room, and everyone inside needs to use the same single key to get in or out. What's going to happen? A huge line forms, right? People end up spending more time just waiting for the key than actually doing what they need to do in the room. That is exactly what happens when a bunch of threads in your app are all trying to get memory at the same time through one single lock, a massive, system-wide traffic jam.
So how do we catch this guy? Well, we have to perform a really deep audit. The sources give us a super clear 4-step investigation. You start broad, with checks on your desktop, then you move to leak checking on an actual phone. After that, you've got to go deep, using native profiling tools to see exactly how your app is interacting with the operating system. And finally, you have to verify that you're meeting the latest, strictest Android memory rules. It's all about being methodical.
And that brings us to our last suspect. This one's been hiding in plain sight the whole time. It's the very framework that's responsible for drawing everything you see on screen. It looks simple, but it has a hidden and very, very high cost.
I mean, just take a simple button. To you and me, it's a button. But to the phone's processor, it's this whole complicated recipe. It's got to draw a rectangle for the shape, it's got to render the text for the label, look up all the right styles, maybe add a shadow effect, all of that for just one button. Now imagine multiplying that complexity by every single thing on the screen. That overhead adds up incredibly fast.
This quote really explains where that hidden cost becomes a total performance killer. Think about a long scrolling list, which is, one of the most common things in any app. Every single item in that list is its own complex styled component. The framework is recalculating and redrawing this whole complicated recipe for every single item as you scroll. It's awesome for flexibility, for making everything look custom, but it is absolutely terrible for speed.
So we've interviewed all our suspects. What's the verdict? Well, it turns out it wasn't just one culprit. The crime wasn't just one bad line of code. The real problem was the entire philosophy of how the app was built. So the fix? It's not a patch. It requires a whole new architecture.
And this is really the key takeaway from all of this. Building a fast app isn't about fixing bugs at the end. It's a set of principles you follow from day one. You have to think in parallel from the very beginning. You need to be deliberate, almost obsessive with how you manage memory. You have to understand the real cost of what you're drawing on screen. And maybe most important of all, you have to measure. Stop guessing where the slowdown is and use the tools to prove it.
And if you need any proof that this way of thinking actually works, just look at this number. The source material points to a performance boost of up to 700% when processing an image. How? Simply by splitting the work across 8 cores instead of loading it all onto one. That's the difference between waiting 8 seconds for an image to load and waiting just 1. That's the incredible power of thinking in parallel.
Okay, so we've solved the case of the slow app. But, this whole investigation brings up a much bigger, more strategic question that every single development team really needs to be asking itself. This goes way beyond just the code.
And that question is this: when does it stop making sense? At what point does all the effort, all the complexity you're putting in to force a cross-platform tool to perform like a native one become more expensive than just building natively in the first place? That's a critical, high-stakes question every team needs to ask about their tech stack. And believe me, there is no easy answer.